Welcome to Virtual Class 17. Today is Friday, May 29th. Hope everyone's doing well and looking forward to an exciting weekend. We have one thing on the agenda today. We're going to go over the review assignments. I'm going to send that out to Kevin in just a minute. I do want to remind you of two quick things. First of all, if you have any assignments that have not been turned in already, please try and do that as soon as possible. I'm going to try and finalize grades while you're working on the exam next week, so we'll only have one thing left to do. And that brings me to the second thing, which is we're taking our exam, remember, on Wednesday of next week. That'll be Wednesday, June 3rd. So that'll be the only thing that we have to do next week. So please prepare for that. It will look very similar to the exam that we took last time. There'll be multiple versions. You'll have a limited time period to complete the exam. You'll complete your work on a separate sheet of paper and submit that separately from the exam questions themselves. If you have any questions, I'm going to have a Zoom session today at 10 a.m. and a Zoom session at 1 p.m. Okay, so I'm going to begin today by sending it out to Kevin, who's going to go over the review assignment for today, the 5 problems, which will look very similar to the 5 problems you'll see on the exam next Wednesday. Take it away, Kevin. Thanks, Kevin. All right, we are about to embark on what is probably the last problem session that I'm going to have with you guys, so it's kind of a little bit emotional. So let's go right to problem number 1. It says the molar heat capacity of tin is 11.1 joules per Kelvin mole. So I'm just going to write out the givens as they are given. 11.1 joules per Kelvin mole. It says how much energy in calories is required to raise the temperature of 25 grams of tin. So 25 grams of tin is the mass. 25 grams of tin from 50 degrees Celsius to 75 degrees Celsius. So temperature 1 is 50 degrees Celsius. That's temperature initial. Temperature final is 75 degrees Celsius. Sorry, just notice that these do have a decimal place there for 3 significant figures. And it says the molar mass of tin must first be found using the periodic table. Convert your final answer into calories using the conversion. Okay, so what we're going to first do is we are going to start off by writing our equation out that we're going to use. So it is Q equals NC delta T. This looks similar, but it's a little different from the specific heat equation. So notice that we're using moles, and instead of using the specific heat constant, we're using the molar heat capacity constant, which is not really that big a difference, but one's in moles. So you'll notice that we are going to have to convert our grams of tin into moles of tin. So if you look on the periodic table, you'll notice that the molar mass of tin is 118.71. So that's grams of tin for every 1 mole of tin. And that turns out to be 0.211 moles of tin. The other thing that I want to point out is the change in temperature. So going from 50 degrees Celsius to 75 degrees Celsius is a change in temperature of 25.0 degrees Celsius. Now, if you go back to the very first day we did this, I feel like I didn't do a good enough job about teaching you the fact that the differences are the same. So what ended up happening on many of your papers is you found the difference and then you converted the difference to Kelvin. What you actually could have done as an alternative, because that was incorrect, was to convert each one of these to Kelvin. So the first one ends up being 323.2 Kelvin, and the second one ends up being 348.2 Kelvin. And when you subtract these two from each other, you get a change in temperature that is equal to 25.0 Kelvin. What I was trying to explain to you on that day is that the changes in temperature are equal to each other. So it really doesn't matter whether you're using units of Celsius or Kelvin because the change in temperature would be the same. This changes by 25 degrees Celsius. If you convert these each to Kelvin, this changes by 25 Kelvin. The one thing that you couldn't do was change it into Celsius or subtract, find Celsius, and then convert that number into Kelvin, because that's no longer a change. Alrighty, moving on. Plugging in our values, we get Q equals. So in this case, my number of moles is right here, 0.211 moles. My value for Cp is right here, 11.1 joules per Kelvin mole. And then my change in temperature in this case is 25 degrees Celsius, which again is equal to 25 Kelvin, which is what I'm going to change it to just so that the units will work out. So I wind up getting a value for Q that is equal to 58.6 joules. And one of the things that I forgot to put on the answer sheet was when you convert 58.6 joules into calories, remember that 1 calorie is equal to 4.184 joules. So you get an answer of 14.0 calories. So that is our final answer. All right, I'm going to pause the video, erase the board, and I'll be right back with number 2. Hi, I'm back with problem number 2. As we go through these problems, I'm going to try and give you some hints, point out some things where I think you might get confused. Make sure that you don't make those mistakes when you encounter this on Wednesday of next week. So the first thing says, how much energy in joules? So we're looking for Q, how much energy in joules is required to change the temperature of 15 grams of water. So the mass that we're dealing with is 15.0 grams of water. And it tells you, and I made a point of making a positive sign there so that way you're not confused. It's starting off at positive 12 and going all the way up to 108 degrees. So temperature initial equals 12 degrees Celsius and temperature final equals 108 degrees Celsius. So in order to go from 12 to 108, you're actually going to go up to the boiling point and then beyond the boiling point. So the problem is going to look similar to this. So we're going to start off here at 12 degrees Celsius. We're going to go up to 100 degrees Celsius. Then we're going to go up to 108 degrees Celsius. And some of you, especially if you haven't watched the video when we did this, are probably wondering, why can't I just go directly from 12 degrees straight to 108? And that's because there are different things that are going on. And when you're going through a phase change, some of that energy is being used to break bonds and not increase kinetic energy, which is what temperature is measuring. So you're going to start here at 12. You're going to go up to 100. Then you're going to go through the phase change at 100. And you're going to go up to 108. So it's actually a 3-step problem. On the homework, we actually had a 5-step problem, which was even more complicated. Also keep in mind, we are going up in temperature. So that means all of our values for Q are going to be positive. Be on the lookout. Some versions of the test are actually going to be a cooling curve. So all of your values are going to have to be negative numbers. So just be on the lookout for that come on Wednesday. So let's look at the first part. So part 1 of this, which is going from 12 degrees Celsius all the way up to 100 degrees Celsius. We have Q equals mCp delta T. Our mass is 15.0 grams. Our constant is 4.184 joules over grams degrees Celsius. And our change in temperature from 12 to 100 is 88 degrees Celsius. Therefore, our value for Q for the first part turns out to be 5,500 joules. So that's kind of Q for part 1. For part 2, when we're going through the phase change, we use a slightly different formula. Q equals mass times delta H. Since we're going from a liquid to a gas, we're talking about vaporization, so we use the delta H of V, vaporization. So in this case, we're going to use, oops, didn't mean to write mass again there. So this time we're going to use 15.0 grams times 2258 joules per gram. Grams will cancel out, and I'll get Q for part 2 to equal 33,900 joules. Number 3, the last part. So going from, so this, by the way, is at 100 degrees Celsius, and this one is going from 100 degrees Celsius up to 108 degrees Celsius. We're going to use this formula again. So Q3 is going to be mCp delta T, but because it doesn't require the same amount of energy to separate gas molecules from each other as it does to separate liquid water molecules from each other, the CP constant is going to be slightly different. So we have 15 grams, that part's consistent throughout the entire problem. The CP for water as a gas is 2.01 joules per gram degrees Celsius, and this time we have a change in temperature of just 8 degrees Celsius. I might keep it as 8.0 degrees Celsius just to maintain two significant figures. So we have Q3, in this case, Q3 is equal to 240 joules. Last thing that you need to do is get Q total. That's just the sum of all three of these pieces. So I'm just going to box them off here. So once you add up all three, I got a total of 39,640 joules. Okay, questions on that? Again, if you have any, Zoom session, 10 a.m. on Friday, 1 p.m. on Friday. All right, I'm going to back out of the way here. I'll let you look at that for a minute. I'm going to pause the video again so I can come back and go over problem number 3. Okay, I'm back with problem number 3. Notice that I've outlined up here our target equation. So this is a Hess's law problem. We're going to try and use these three to come up with this target equation. So when I look at these problems, the first thing that I try and do is to find something up in my main equation from this first set here. So I have HF. I have HF up here. It doesn't appear anywhere else. So I know I need to get two HFs. It's on the right side of the equation in both spots. So that's correct. So I don't have to flip the equation, but I will need to multiply it by 2. So I'm going to multiply everything by 2. So a half of an H2 becomes H2. Half of an F2 becomes F2. And then I get 2HF. And then my delta H remains negative and becomes negative 546 kilojoules. So the only thing I had to do here was multiply by 2. Okay, if I look at my second equation, I'm not going to look at S, not going to look at F2 because that's involved in multiple spots, but I can look at SF6. I have one SF6, sulfur hexafluoride, on the right side, and I have one sulfur hexafluoride on the right side. So I don't need to do anything to this equation. I could just recopy it along with its delta H value. So I get S plus 3F2 goes to form SF6, and the delta H equals negative 1,220 kilojoules. So I'm just going to put a note here, leave alone, so don't do anything to that. And then finally, looking at my last one, I have H2S. I have H2S over here. It has the correct coefficient, 1, but it's on the wrong side. So I'm going to take this entire equation, I'm going to flip it around. So I'm going to get H2S goes to form H2 plus S. And because I flipped the equation around, I changed the sign on delta H. So it was negative 21 kilojoules. It is now positive 21 kilojoules. So let's take a look and see if I've done everything correctly. So crossing things out. If you notice, first thing that I can cross out, I have H2 here, H2 down here. And get rid of those. Next thing, I have, let's see, an S, a sulfur atom here and here. I can get rid of those. I have fluorines, but they're on the same side. So instead of crossing them out, these are going to get added together. So if I put back everything that I have left, I have H2S plus 4F2, 3 plus 1, going to form 2HF plus SF6. So because this equation matches the target equation that I was looking for, that means I did everything correct. So the only thing I have to do now is get my delta H for the reaction, which is what you get by adding all those up, and you get negative 1,745 kilojoules. All right, good stuff. On to problem number 4. Okay, I am back with problem number 4. Now I'm going to give you a piece of advice. You could take it or leave it. When I go through and do these problems, I kind of set them all up simultaneously because I'm flipping through this packet. I might as well just identify all 3 values just the way they are. So I'm going to start all the way on the left side here. My delta H at standard conditions, my delta G at standard conditions, and finally my delta S at standard conditions. So remember first that you start here with the products. You do products minus reactants. So start on the right side. So for delta H, I look that up and I have negative 106.7 kilojoules per mole. Now, notice coefficient here is 1, so I don't have to multiply that by anything. Then I'm going to go straight down the list. Negative 64.0 kilojoules per mole and 309.4. Notice this unit is different, joules per Kelvin mole. All cases, I have a coefficient of 1, so I don't have to do anything there. So now I'm going to add, it's on the same side, you add the 2 together. So I'm going to add to this my 3 values for hydrogen as a gas. So I go through my paper and I find hydrogen as a gas. By the way, if I forgot to mention it earlier, when you're looking up CCl4, look under carbon. And the reason it's under carbon is because carbon is the central atom. So look under carbon. Okay, on to hydrogen. So my values for hydrogen. Well, hydrogen is an element in its natural state. So the value for delta H is going to be 0, multiplied by 2, but it doesn't really matter. My value for delta G is going to be 0, multiplied by 2, but it doesn't matter. And my value for S is actually 130.58 joules per Kelvin mole. I'm going to have to multiply that by 2. Okay, next. Now I'm going to jump to the reactant side, so to the left side of my equation. So I'm going to subtract everything that's on the left side. So let's take a look at that. So I'm going to start by looking up the values for methane. So I have negative 74.8 kilojoules per mole. Again, the coefficient is 1 here, so I don't have to do anything over here. The next one is negative 50.8 kilojoules per mole. And the last one is 186.3 joules per Kelvin mole. And they're on the same side, you add them. So I'm going to add the value for chlorine. Chlorine is another element in its natural state. So it's going to have 0 kilojoules per mole for delta H, multiplied by 2. It's going to have 0 kilojoules per mole for delta G. Again, multiply it by 2. And then the value for S is 222.96 joules per Kelvin mole times 2. Okay, so I calculate all 3 of those. So for the first one, I get negative 31.9 kilojoules per mole. The second one, I get negative 13.2 kilojoules per mole. And for the last one, I get negative 61.7 joules per Kelvin mole. Now, in the actual instructions for the problem, after you get delta H, delta G, and delta S, it wants you to verify those answers, just like we did on the homework assignment. So you're going to use this equation to verify them. Delta G equals delta H minus T delta S. All of these are at standard conditions. That basically tells you that you can use a temperature of 298.15 Kelvin. So I'm going to take my value for delta G, negative 13.2 kilojoules per mole. I'm going to set that equal to my value for delta H, negative 31.9 kilojoules per mole, minus my temperature, 298.15 Kelvin. And then I'm going to multiply it by my value for delta S. Now, be careful, because you can't just throw delta S in there the way it is right now. You have to divide your delta S value by 1,000 in order to convert it from joules per Kelvin mole into kilojoules per Kelvin mole. So this is going to be negative 0.0617 kilojoules per Kelvin mole. Negative 0.0617 kilojoules per Kelvin mole. And the reason why you have to do that again is so that the units of kilojoules per mole will work out. Okay, when you type that into a calculator, you wind up getting negative 13.5 kilojoules per mole, or what I like to call, and what some of you call close enough. So there's some rounding issues and things like that, nothing to be concerned about. If you got an answer of 50, then you would be concerned. But being off by a couple of decimals, by a couple of tenths actually, is not anything of concern. All right, so there you have problem number 4. We had delta H, delta G, delta S. We solved for each of them, and we plugged them into this equation to verify. I'll be back with our last problem, which is problem number 5. Okay, I am back with question number 5. So question number 5 presents us with 2 different diagrams, a phase diagram and energy diagram. I'm just going to go through a couple of the important points here. So if you notice, I have labeled A, B, C, D, and E as 5 different changes. So letter A, this is going from a liquid to a solid, so you can call this freezing. I've also heard it referred to as solidifying, so becoming a solid. Either one of those would be fine. Going from a liquid over to a gas for B, this is called vaporization. C is going the opposite of A, so from a solid to a liquid, this is called melting. D is going from a gas to a liquid, so this is called condensation. Letter E, going from a solid to a gas, is called sublimation. Now, there are 2 other important points on here that I want to make sure that I mention, which might be on your exam, even though they weren't one of the 5 that I identified here. This point right here, remember, has a special name. It's called the triple point. It's called the triple point because all 3 phases of matter, solid, liquid, and gas, can coexist in equilibrium. The other change that I didn't have an arrow for here, so that would be going this way, this is called deposition. So going from a gas directly to a solid, not something that you see very often, but it's possible. Okay, the last energy diagram, the one on the right here, I'm going to go over these changes. So first of all, you'll notice that this is an exothermic reaction. Exothermic because at the end, you have less energy than you started with. So you started with this amount of energy, you finished with this amount. Because energy is given off, that's exothermic. An endothermic reaction would have been start off with a certain amount of energy, you have a activation energy barrier just like you do here, and you would finish higher than you started. That would be endothermic. Okay, so this is called the energy of reactants. D is called the energy of products. I mentioned earlier, this is called the activation energy. And then, as I said, the difference between where you start and where you finish is called the energy of the reaction. So it's a subtle difference between reactance and reaction, but it is there. So be prepared to identify a phase diagram like we have over here, or an energy diagram like we have here. Make sure that you know what it would look like if it were endothermic instead of exothermic, and you would label the same parts. Right, I'm going to send it back over to the desk to Kevin, who is waiting by for closing our final video together this year. See you guys. All right, thanks, Kevin. That brings us to the end of our virtual classes. Obviously, this year did not turn out the way that anyone had thought. I don't think there's anyone that could have predicted that we would be spending the last 12 weeks of school communicating from home. But it does serve as a life lesson to make the most of whatever cards you're dealt. Obviously, no one would prefer this, or actually maybe some of you would, but anyway, it has been an incredible year. I don't know if I'm going to make another video because it'll probably be too emotionally taxing to go through and say exactly what I want to say to each one of you, but it has been an incredible year. I'm extremely fortunate to have you guys in my class. I enjoy doing this very much, not so much this, but normal class. And I will miss all of you guys very much over the summer. So please try and keep in touch. If you have any questions or anything, obviously feel free to email me at any time. And I hope everyone has a very enjoyable summer. It's been a great year. So I hope everyone stays safe, goes outside, and has a lot of fun. I'll see all of you next year in September, hopefully in the hallways. But until then, have a great summer.